Introduction to related rates. Goal here, just one, understand how to set up and solve a related rate problem. These problems can be challenging, and there's some key aspects to kind of grab onto, but every related rate problem has potential of being different than the one that came before it. So you really have to kind of grasp onto some key elements as you're setting these up, and just focus on making sure you're doing those. And then, even if the problem is different, you will tend to get to the right answer. So overall, related rate problems, they typically involve two or more related variables that are changing over time. So for example, the volume of water pumped into a water tank and the height of the water in the tank are related to each other. The faster the water is pumping in, the faster the height of the water in the tank is changing, and vice versa. The slower it's going in, the slower the height is going to change. So there's other things that go along with this in this example, but this is essentially what we're going to be looking at overall. Is we have maybe volume and height related, and we want to maybe find the speed at which the height is changing. We'll see that in the first example that we're going to work out. So all these related rate problems have this kind of element where variables are related to each other, they start changing, and you want to find, with given information, how one is changing. Or maybe a couple, but usually just one. So our goal is to find a way to relate these rates to each other via an equation. So setting up an equation that relates these variables together is huge. Then we're going to use the chain rule concept to find an equation that relates the changes over time. So we're actually going to derive the whole equation relative to time. So the chain rule is going to come in, and in a sense, in a roundabout way, that implicit differentiation idea. And finally, we will use the equation that we got with that derivation to solve for the desired value. So let's take a look at an example. So we have a cylindrical cylinder with radius 5 meters is being filled with water at a rate of 3 meters cubed per minute. So that's a change in volume there. How fast is the height of the water increasing? So how fast is the height of water increasing? Our goal here then, what we want, if we're using the variable h for height, we want dh dt. That's our goal. So let's try and get our mind wrapped around what was given here. We were given a radius 5. So r for radius will equal 5. I'm not going to bother putting the units at this point, since everything that's been given is meters or minutes. I'm not going to worry about writing the units because they're all the same. And they also gave me it's being filled with water at a rate of 3 meters cubed per minute. Meters cubed is a volume. So it's a change in volume over time. They're actually giving me a dV dt. And this is going to equal 3. So these are some of the pieces. We want dH dt, and all they've given me is r is 5 and dV dt equals 3. So one of the first things we're going to do before we actually set the equation, draw a picture. And a lot of these, if you don't draw a picture, it's really hard to visualize what's going on and create an equation. So cylindrical cylinder, we have radius of 5. We don't know the height here. They didn't give me any information about the height. We'll see if that's needed. Sometimes it's not. Sometimes we just got a bad problem. But hopefully this one isn't a bad one. So let's try and find a way to relate this 5 radius, or more importantly, the radius and the height and the volume together. Since they're giving me a change in volume, they're giving me a radius, I want a height change. I got to find a way to relate those together. So looking at this cylinder, we do have an equation for the volume of a cylinder. And that volume equation is the pi r squared, which would be your area of the circular base, cylindrical base, times the height. So once you have an equation set up that relates the variables of interest, the height, the radius, the volume in this case, now we're going to take this equation and derive the whole thing with respect to time. So I'm going to take d dt of this whole entire equation. So on the left side, I'm just going to get dv dt. On the right side, I've got a couple of variables multiplied by each other. Got to use the product rule. So I'm going to focus on the r squared first. The derivative of that is 2r. So I'm going to have pi. I'm just going to write this out kind of in this order. So pi times 2r times h, and then dr dt. We derive the r, which is some unknown function of t. That's where the implicit chain rule idea comes in. And that means we got to multiply by that dr dt at the end. So then plus, now I'm going to derive the h. So the pi r squared just carries along. The h goes to 1, but since I'm deriving something that's some unknown function of t, I'm going to multiply that by the dh dt, complete the chain rule there. So now let's take a look at this and see if there's any simplifying that can be done. And one thing to note, the radius doesn't change. This cylindrical tank, it's not growing in size relative to its radius. It's a tank. It's a cylinder. Radius isn't changing. So really that dr dt in this case is 0, which is nice because that allows me to not have to worry about what the height was. So 0 will actually get rid of that whole first part of that result for dv dt, that whole first term essentially, and we just get pi r squared dh dt. And that's looking good. I'm liking where that's going because I have all the information. I got a dv dt that was given, I have an r that was given, and I want dh dt, which I can solve for. So I'm going to do a little solving here, move the dh dt over to the left side and essentially divide out the pi r squared. So we get this dv dt divided by pi r squared would give me the dh dt. And now dv dt was given as 3 meters cubed per minute. The pi just stays. The r was 5, so we'll have just 5 squared. And when you work that out, you get approximately this 0.038. And this would be meters per minute. So the change in the height in this case is 0.038 meters per minute. And notice again, we took the information that was given, looked for an equation that related the variables, the height, the volume, the radius, based on our given description. And then you just derive that equation with respect to time, because things were changing over time. And we used some, just a little bit of intuitive fact, this idea that the radius wasn't changing to help bring that equation down to something manageable. And thankfully, it brought it down to something that used all the given information and allowed us to solve for the desired value. So let's see another example here. So this one, we got a street light mounted at the top of a 15-foot tall pole. A man 6 foot tall walks away from the pole with a speed of 5 feet a second along a straight path. How fast is the tip of his shadow moving when he is 40 feet from the pole? Well, I'm going to go ahead, again, draw a little picture here. So let's say this is the light pole, 15 feet tall, light at the top. Man 6 feet tall is walking away. I'm going to draw this, man walking away a little further away just so I can get a shape here. And the tip of the shadow is going to be cast by the light shining down. And if I draw this, looks like I've created a triangle here. And in fact, if I kind of focus on this little triangle here, it's similar to the bigger triangle that has the 15. So I got to find some way to relate that stuff together. And let's go ahead and put some other variables in here, because the distance that the man is away from the pool, that's going to be changing. I'm just going to use a variable for this. You don't want to plug in the 40 right away. If you do that, you start deriving things, it's going to go to 0. So you don't want to plug in these kind of given fixed values too early. It's just like on the last example where we had that radius of 5. I didn't plug that in right away, even though it wasn't changing. I didn't want to accidentally get rid of it too early. So I always wait and plug in these given fixed values later. So I'm just going to call that X is the distance the man is from the pole, and then the tip of the shadow way out here would be another distance Y from that man over to the tip. So what we really want here in this case, how fast is the tip of his shadow moving? So we want the ddt of this X plus Y distance. That gives me the tip of the shadow from the light pole. What are we given? Well, we got the 15 foot, the 6 foot already in the picture. We got those there. Oh, and then it's telling me that he's moving away from the pole 5 feet per second. So that's really the change in the X. So we're given dx dt is equal to 5. I'm not going to bother writing the feet per second here. And then we're also given that X at some point is going to equal 40. All right, so from here then, it's like, okay, I'm looking for an X plus Y change. And that means I need a way to relate X plus Y to everything else that's going on. And more importantly, I want some way, since I'm being given dx dt, I'm given no information about the dy dt. So if I derive this right now, this ddt of X plus Y, I'm just going to get 1 dx dt plus 1 dy dt. And I have no information about the dy dt. So what I'm going to try and do here is get this ddt of X plus Y to just be in terms of X, because that's all the information I'm being given at this point. So that's kind of the thought process that you need to go through. What am I given? What do I need to get rid of? And this is a problem where with the similar triangles, it's kind of a classic type of these related rates. I'm going to say, okay, well, 15 over 6, those, kind of left side, so to speak, of the triangles would be equal to the bottom side of the bigger triangle is X plus Y. If you want to relate that up or, put that across from the 15. And then the smaller triangle, we just have Y here. And we get the 15 sixth Y equals X plus Y. And then 15 sixths Y minus Y equals X. And simplifying, you would get 3 halves Y equals X after you do the math on that left side and simplify. And I have information about X, so I want to find a way to replace Y with something. So I'm going to solve for Y here and get 2/3 X. Okay, so from there then, I'm going to set this up, this ddt of X plus 2/3 X. Simplify, you're going to get ddt of 5/3 X. And taking the derivative now, we get 5/3. The X goes to 1, and then dx dt. And in this case, notice we didn't even need the 40. Sometimes that'll happen. They'll give you extra information. So I just plug in the 5 that was given for the change in the X part. And I get 25 over 3. And this would be feet per second. So the tip of the shadow is moving at 25 over 3 feet per second. All right. Thank you for watching.